With my double blade axe and my hobnail boots, I go where the timber.
Hello and welcome back to another fun and exciting lesson in Algebra 2. This is Mr. Bean. Today's lesson is on an introduction to logarithms. And we have here Paul Bunyan accompanied with our Paul Bunyan theme music. And I got Paul Bunyan here because he's a lumberjack. And you see what I did there with that? Put lumberjacks and logs. See how that goes in hand in hand? And I found this picture of Mr. Kelly who looks like he's a lumberjack or something in this. I don't know what in the world's going on with this. It's a crazy beard he has there. They do have some things to do with earthquakes and sound and some other cool application problems, which we will get into a little bit more in our future lessons. But for today, we're going to skip this part for now. I will come back to it, so just remember to come back to this beginning of our notes as we talk about applications. So what do we know here? I wanted to talk about how do we solve x equals 3 squared. That is something that you will be familiar with. That's real simple. It's just x equals 9. Okay, we can do that. We know how to. But what if we don't know what the exponent is, 3 raised to the x? This is something we haven't learned how to do yet. And so with the introduction of logarithms, this is the beginning of how to solve for an exponent when we don't know the exponent. Okay, so what I think about is if we had addition, if we did the inverse of addition, that would be subtraction. If we have multiplication, I'll use a dot for multiplication. If we had multiplication, how do we undo multiplication? We would use division. They're like inverses of each other. And so that's the same way with exponents and logarithms. They are inverses of each other. And so it's very important to know how to use logarithms to undo exponents. Okay, it's kind of cool stuff that we're going to be doing today. And a lot of people get a little bit nervous with it because it looks so weird, but don't worry, this is not hard. So it's just new to you. So here we have this blah blah stuff. Y equals log base b of x if and only if b raised to the y equals x. Okay, this is a lot of information to take down here. This one on the left is what we call logarithmic form, and the one on the right is exponential form. So make sure you get that written down. I have some little clarifying statements down here below that have to be true, and that is that the b, the base, has to be greater than 0, or this stuff doesn't work. Okay, so the base of the logarithm here and the base of the exponent will both be greater than 0. They cannot be the number 1. And what else? That the x values are going to be larger than 0 when dealing with a logarithm. Okay, so the x values that we plug in here will be greater than 0. It doesn't work with negative values. After you've got that down, now let's jump to this. How do we say it? If you don't say it right, then people don't know what you're talking about. For instance, if I have this, this is different than this. Okay, so if somebody says log 2, then this is a very specific number. We'll get into what this means later. But if they say log base 2 of x, that's something completely different. So be careful the way you say it. You have to say log base b of x. Okay, so in fact, if we were all in a class together right now, I would make you all repeat it. So maybe you've got a little brother or sister walking around you, or your parents are making dinner as you're doing this, but say it out loud anyway. Okay, you ready with me? Here we go. 1, 2, 3. We're going to say this. 1, 2, 3. Log base b of x. All right, very good. Now you look kind of weird, so let's just get back to work here. Number 1, we're going to rewrite this into exponential form. Starting off with logarithmic form, and we'll do exponential. So the way this works is, if we look back at our little notes here, notice that the bases are both bases in the logarithm and bases of the exponent. And then it's going to rewrite this as b raised to the other side. So it's going to be the base is 3, so it's 3 raised to the other side, which is a 5. That will equal 243. This is now exponential form, and this is true. 3 raised to the 5th power. If we did that in a calculator, we get 243. Okay, number 2. The base is a 5. We're going to raise it to the other side, which is a 3, and then 5 cubed will equal 125. That is logarithmic form. See, so easy. Okay, now you can do this on your own. Pause the video now. Do numbers 3 and 4. And here are our answers to numbers 3 and 4. 9 raised to the 0, so the base is 9, will equal 1. And 1 half raised to the negative 4 equals 16. This one here on the left will give us an interesting property, and that is if we take the logarithm of anything, you might write this in the margin of your notes, if you have the log base b, so instead of base 9, log base b of 1, that will always equal 0. Now, why is that true? Because if we do some unknown number b raised to the 0, it always equals 1. Okay, so this is a nice property right here that you could have on the side of your notes, that if we're taking a logarithm, base anything of 1, it equals 0. Here, this one, I like these because it throws in this negative exponent stuff where you have a negative exponent, meaning that takes the reciprocal. So this is the answer for this problem, but but what I'm about to write down, don't write this part down. I just wanted to show you that if you simplified this, it would become 2 to the 4th power. If you got rid of the negative, you take the reciprocal, and then 2 to the 4th power, of course, is 16. Remember our applications at the beginning, earthquakes and sound? Let's talk about that for a minute. First thing we have is what's called the Richter scale. That's going to go in your line number 1. And the Richter scale is dealing with earthquakes. Here we have an earthquake that occurred in Japan on March 11th, 2011. If you remember, this is the famous earthquake that created that large tsunami that devastated northern Japan. You can see here just the bus shaking and this truck shaking back and forth. Pretty powerful stuff. And here we have a video camera outside a swimming pool near Mexico City. Let me fast forward this a little bit. You've got an earthquake that hits, and there we go. Now the earthquake's hitting, and you can see how powerful that is. It's just going to make this thing shake back and forth, back and forth. Amazing stuff. I like to say it's an earthquake, or after holiday season and all those meals, it's Mr. Brust maybe jumping in for a swim. Really, Brust is totally in shape. He runs to school or bikes to school like every day. The guy's a monster. But it's still a funny joke. And so if you should have this added to your notes, that you have something about earthquakes, and that is using a measurement called the Richter scale. All right, we'll come back to more later. Now let's rewrite these in logarithmic form. So now we're starting with exponential, and we'll rewrite it. So we have log base, what's the base of the exponent here? It is a 3, so we'll say log base 3, so we'll write a little bit of a smaller 3 down here, and then of 9 equals 2. So if you remember, it's 3 raised to the 2nd power gives you 9. 3 squared equals 9. This is how we rewrite that. So here, number 6, log base, what's the base of the exponent? It's a 2, so it's 2 log base 2 of the other side, which is 32, equals 5. So this means 2 raised to the 5th power equals 32. That's the logarithm form, logarithmic. All right, do numbers 7 and 8 on your own. Pause now. Number 7 goes back to our property that we wrote earlier with number 3, and that is if you have log base 5 of log base anything of 1, it equals 0. So the base here was 5. And in this one, it was kind of cool because you had to figure out that this cube root stuff means 64 raised to the 1/3. Remember that from Mr. Sullivan's lessons? Hopefully we've got that down. And then we'd have, so therefore log base 64 of the other side, which is 4, equals our exponent of 1/3. Now, before we go on with the rest of the lesson, I need to point out that you should not be using a graphing calculator on most of the things we're doing for here on out. Now, there may be a couple things I point out specifically that it's okay, but most of this, like the graphs and figuring out logarithms, you'll be expected to do this without a calculator. Number 9, now we will evaluate. Evaluate is another fancy word for just kind of like saying simplify the thing. You know, like if I said 2 plus 3, evaluate, what is that? It just means give you the answer. It's 5. So when we have our logarithms here, we're just talking about what is this thing? Without having to grab a calculator, can we figure this out? Sure, it's not too bad. We don't know what it equals, so what we'll say is it's, I'm just going to say that it equals like some question mark, or you could even put a variable like maybe an x. So we will say 2 raised to that question mark, or an x if you wanted to say x, 2 raised to something equals 8. So what does our something have to be? What does this something equal in order for this statement to be true? Our something would be 3. So the answer to this thing is 3. So if you can kind of squeeze in some of this work here, I know that's a little bit tight in your notes, this whole thing equals 3. Now let's do this one. So this time I'll use a variable instead of a question mark. I'll say that it equals x as we're trying to evaluate this. So 7 raised to some unknown variable is going to equal 1/7. So we take the logarithmic form, transfer it to exponential form. How can this possibly be true? What exponent would we need? And this is where you kind of have to think about your rules, use your head a little bit, think through it, and you'd have to come up with that the only thing that can make this happen is if your exponent is a -1. So we have log base 7 of 1/7 equals a negative 1. Okay, so that little x here that I'm throwing on, that's extra. I threw that in there just to help us solve it and to transfer it to exponential form, but really it doesn't really belong. This thing equals negative 1, not x, just equals negative 1. All right, why don't you try 11 and 12 on your own for some good practice. Pause now and I'll have the answers appear. Here's your answers to number 11 and 12. Number 11 was a negative 4. Number 12 was a 1/2. I'm going to explain this for a minute. If you got these answers, you could skip ahead a little bit to the next part, but I want to make sure I've gone over how to do this. This one is pretty tricky. So you have 1/3 raised to some unknown equals 81. What I did is I took the reciprocal because I can get 3 to 81 a lot easier than 1/3 to 81. So if I take the reciprocal, then I'm going to make this exponent a negative. So how do I make this exponent up here would have to become a 4 in order to get 3 to 81. 3 raised to the 4th is 81. So what I'm going to do is I'm saying this entire exponent, negative x, is going to be 4. That's what this next line shows. And then therefore solve for x, and it would be negative 4. So that, again, the negative exponents will create the reciprocals where you flip the thing around. All right, number 12. How do we get 25 to become a 5? How do you get it smaller with an exponent? The way you do that is with a radical. So if I took the square root of 25, that would be 5. So square root of 25 is the same thing as 25 to the 1/2, and that's where the 1/2 comes from. Okay, so yeah, you actually have to be good with your rational exponents here with logarithms too. All right, go back to our application. So after earthquakes and Richter scale, what's another thing we've got? We have what's called the decibel level. This is the beginning of your notes again. So with decibel levels, so one thing we've got with decibel levels is crickets. So add into your notes now the sound. Sound can be measured with something called decibel levels, and that involves a lot of logarithms going on there, which is kind of interesting. Didn't know about that, which we'll talk with again in another lesson later on, how that works out a little bit more. Now we're getting into two things called common logarithms, natural logarithms. These are the most common logarithms that we work with. Common, okay, that's kind of funny. I didn't mean to say that way. Common logarithm is basically the logarithm is base 10. When you have logarithm base 10, we write it shorthand like this, log x. If you ever see log x, it's not that the base is gone, it's just that the base is a 10. We assume it's 10. For a natural logarithm, we have log base e, natural number, okay, log base e, but we don't write log base e, we do this ln thing. I don't know why it's not NL instead of LN, because it's called natural log. You'd think we put the N first. I think it has something to do with the Latin way that you say this, like log natural or something like that. I don't really know. So why are these things important? Well, there are several reasons and uses that they have, but one of the reasons is that we can more easily and readily use them with our calculator. If you look down here on our calculators, we have these two buttons right next to each other, log and ln. That's our common logarithm, a base 10 logarithm, and a natural log. So here, to just test that out, if I do log 10, what that means is it's log base 10 of 10. And if you enter, it should just be a 1. Or if I do log of 100. Think about that. If you should know this already. If the base is 10, 10 raised to what power gives you 100? It's 2. So that would be a 2. Same with natural log. So if I took the natural log and then did the letter e here, second division, then the natural log of e, that would also be the number 1 because the log is base e. Okay, hopefully that makes sense with common log and natural logs. And so for numbers 13 and 14, we're just going to do some quick calculator use, and that is just type them in your calculator. So if you don't have a calculator, grab one, plug these in, and let's see what you get. I'll have the answers pop up here in just a sec. And there's our answers, and I went to 3 decimal places because it's typical in like our AP mathematics classes that you go to 3 decimal places when we are rounding our final answers. And so where did I get that? I just plugged it in the calculator here. See, simple, log 13 and natural log of 6. That's where we get them. Okay, let's jump into, we're getting closer to the end of our notes. That is things that simplify. It's a couple of little basic logarithm rules. If you have, and I showed you this a little bit with the calculator, if you have the base of the logarithm and you're taking a base of with an exponent and they're the same thing, basically it's kind of like this whole thing just goes and cancels, and all you have is x. Okay, let me make that sound again for this one. See, base is the same, but now the exponent has a logarithm, but if the bases are identical, it just kind of like it cancels and it has an x. Okay, so look at number 15. We have 10 log 6. This cancels. Why is that canceled? Because the base of the logarithm is a 10. You don't see it, but remember this is a common logarithm. And so the answer to this thing is that it equals 6. All right, how about this one? Well, if we simplified this, I'd actually want to rewrite it. So if I have a base 3, let's rewrite 9 so that it's 3 squared. And then raised to the x. If we raise that to the x, that just means 2 times x. And so the log base 3 of 3 cancels, and all you have left is 2x. Okay, so if you don't have bases are identical, you try to rewrite it so that they are. If possible. And we give you some nice cookie cutter problems so that it will work out that way. If not, then you'd have to use a calculator to help you. Why don't you try 17 and 18 on your own? Okay, and you should have gotten that this one is 3x because it's e and natural logs have the same base. And then number 18, again, natural log and e, same base, log base e of e. And so all you would have left is x over 2. We're just simplifying this, okay? It's a variable. So there's nothing to solve. There's no equal sign here, so don't get confused with that. All right, done with that. All right, now what in the world was that? That was just another example of decibel levels, okay? Just had to throw one more in there. Jet engine, super loud, so that would be the more extreme loudness of decibel levels that would really hurt your ears because they get so loud. Okay, last part of our lesson, and that is dealing with graphs. How you doing? You holding in there? I know this lesson's a little bit long, but we got a lot of information we're covering. Graphing. Let's first look at the exponential curve. You see here we've got our exponential curve. It goes through the points 0, 1, 1 comma b, whatever the base was, when it's just a normal old b raised to the x. And we'll say, so the a here is a 1, so it's a 1 in front, 1 times that. And that's where the exponential graph comes from. Well, if the logarithm graph is an inverse graph, that means we can flip it across this line, this y equals x line. It's a reflection point. Or in other words, we can swap the values. So we swap the xy values. That's how we get inverse. So that means it's going to have a coordinate point right here of 1, 0. In fact, let me switch colors. There we go, green. That's pretty. Okay, so then we have 1 comma 0. 1, 0 is the coordinate point for the inverse of this, and then it would be b comma 1. So whatever b comma 1 is, it depends on what b is. We'll just put it right here. Wait, what is this b? That b is a 2? Yeah, that works. So we'll say this one is b, whatever the base of the logarithm is, b comma 1. And then you'd have this graph that looks something, oh man, my hand got bumped. Something like this. Okay, it's supposed to go down here. So originally on the exponential graph, we had this horizontal asymptote that comes across here. On a logarithm graph, you get a vertical asymptote straight up and down, and it's always going to go through these points. Let's do the next one. So the previous example, this was dealing with an exponential growth, and we reflected it to get a logarithm graph. Now we have an exponential decay, and the base is in between 0 and 1. So what does that type of logarithm graph look like? Let's flop these points again. So it's going through 0, 1, so we'll go here and make this become a 1, 0. And then what about this other point? Okay, so in this instance, this b value, the y value, is a half. So I'm going to come out here now to a half and up to 1. This looks a little bit crazy here. So I've got b comma 1. And what this is doing is it's approaching a vertical asymptote here, and it's coming off like this. Okay, that looks craziness, but that is what's going on with the logarithm graph when the base is in between 0 and 1. Be careful not to think that there is a horizontal asymptote right here. There is not a horizontal asymptote right there. That's wrong. But there is a vertical asymptote straight up and down for logarithm graphs. Let's do a couple examples of graphs now. What I'd like you to do to start us off is I want you to draw something like this in the margin, a t-chart. So way off on the left side of your notes, let's draw this thing, and then above it put down y equals log base b of x. And the reason I want you to do this is so that we can say any base. So instead of a base 4, we're going to do a base b. Again, this is on the side of your notes. We'll come back to this in a minute. Well, if I can plug in a b raised to anything I want. Let's just say, for sake of ease, a 0. Well, then that means I would have log base b of b to the 0. What does that equal? Log base b of b cancels, and you get 0. Okay, well, now let's do this one. B raised to, plug in a different number. How about b to the 1? Then when we would get a log, oops, that's supposed to be log base b of b to the 1. Well, what does that equal? Log base b of b cancels, and you get a 1. If I plugged in a b squared, I'd get a 2. If I plugged in a b cubed, I'd get 3. Oh my goodness, can you see the pattern? If I plugged in a b to the 100, you'd get, you guessed it, 100, okay? So what you plug in for a t-chart depends on what the base is. You're just going to plug in whatever the base number. In this first example, it's going to be a 4, and you're going to plug 4 to the 0, 4 to the 1, 4 to the 2, and so forth. All right, so let's do that. So get rid of this. This should be on the side of your notes. I'm now going to fill in an example for number 19, and that is going to be, let's plug in the number 4 to the 0. So plug in a 4 to the 0 here, and what do you get? Log base 4 of 4 cancels, and you get 0. Then we plug in a 4 to the 1. 4 to the 1, so we'll change this, and that's a 1. 4 squared, and that's a 2. 4 to the 3rd, and that is a 3. Now here, whatever these numbers are, well, what's 4 to the 0? 4 to the 0 is just the number 1, so x is a 1. 4 to the 1 is 4. 4 squared, well, that's a 16. And 4 cubed is a big number. 64, I think? Yeah. Big number, it's going to be way off our chart, so we don't really need to worry about that. Same with 16. But the idea was you just use the base. So our first coordinate point, 1, 0. We go 1, 0, put a dot. The next point, 4, 1. 4, 1, put a dot. The next number, 16, 2. So we'd have to go way off this chart over here and then go up 2. What if I went this direction? Well, I could. Remember on our examples that I was showing, if we go back here, these examples, these logarithm graphs are actually never going to go negative. So we have a vertical asymptote right here up and down. Let me draw that thing. We have a vertical asymptote right along the y-axis. So this graph, once we just have a couple points here, you can sketch this graph, and it is approaching that vertical asymptote. Oh, that was a pretty bad sketch, but that's close enough. Okay, you could plug in, of course, 4 to the negative 1. Oops, 4 to the negative 1, and that would give you negative 1. Well, 4 to the negative 1 is the same thing as 1/4. So that's another coordinate point, 1/4, negative 1. I could go 1/4 down to negative 1, and it would be there. So if I graph that correctly, it would go through that point. So that's another way of getting some points that are closer if you wanted to use negative values for your x. All right, what's the domain? It's all the x values that are greater than 0. We don't say or equal to 0 because we have a vertical asymptote here. It's not actually going to get to 0. It's all the values that are bigger than 0. And the range, well, it's all the y values that go down to negative infinity and go all the way up. It does slow down, but it goes on forever. So the range is all real numbers. Okay? Now, when we start shifting things, it is exactly like we've shifted things for the entire year with our translations. Okay, so just a quick little reminder that we shift the opposite of what's on inside the parentheses, left and right, and then outside the parentheses, we're going to go up and down whatever that value of k is. So here we go. Let's first figure out some coordinate points before this thing is shifted. So, in other words, ignore the +2 and the -1 that's inside there for just a moment. Log base 3 of 3 to the 0, if we plug that in, we get a 0. Plug in a log base 3 of 3 to the 1, if we plug that into this x, you get a 1. I'm choosing, remember, the base 3 because the base of the logarithm is 3. Now we plug in a 3 squared, and we get 2. And that's about as far as we need to go because 9 for an x value is way off the grid, so it doesn't make much sense to go too much further. Okay, now we are going to shift it to get our new values for x and y of what the translated graph is. So let me erase that so you can see it again. And what are we doing? We're going to subtract 2 from all the x values, and then we're going to subtract 1 from all the y values. Remember, we're doing the opposite of the inside and then we go down 1. So what happens to that? So this is a 1, and then we subtract 2, you get -1. This is a 3, you subtract 2, and you get 1. This here is a 9, subtract 2, we get 7. And now we take these values, 0, 1, 2, and subtract 1 from each of them. And it becomes those. All right, now let's get our vertical asymptote. Where's that vertical asymptote? It's usually on the y-axis, but this shifted over left 2. Okay, so you just have to kind of carefully think through how we shift things. So there's the vertical asymptote. Again, used to be on the y-axis, shifted left 2. And now let's plot some points. So here's our new points. We go -1, -1, and 1, 0, and 7, 1. So 7, 1, 5, 6, 7. It is off the graph a little bit, but I'm going to put that point there anyway just because it will help me sketch a graph of this thing. And it should be approaching that asymptote, curves off. Oh my goodness, that was horrible. It's supposed to be a little bit smoother than that. And there is our logarithm graph. Again, it is not existing on the left side of this vertical asymptote. The domain is all the x values that are greater than -2. And the range is everything. It goes down forever and up forever. Hey, you survived your introduction to logarithms. Big appreciation here to Kelly Bunyan, who helped us out getting through the... Okay, I don't know. This is just dumb. It's just because it's anything I can do to try and make fun of him somehow. And I just thought that was funny with his original picture. All right, hey, this is Mr. Bean signing off. Rock that mastery check, and I will see you in the next lesson.